So we're going to discuss something called Wick's theorem. Which is just sort of going to formalize some of these kind of calculations we're doing to compute scattering in quantum field theory. So remember what we've got. We've got that the unitary operator that leads to time evolution in the interaction picture is the time-ordered exponential of this object, the interaction Hamiltonian in the interaction picture. Okay? So this was the solution to, well, this was basically Dyson's formula, the solution to the Schrödinger equation in the interaction picture. Okay. Bruno asked me this question yesterday when we were doing this particular example for meson decay. I'd written down a particular h int. So this is slight aside, but yesterday I wrote h int equals g squared psi star psi phi, and plugged this into this equation. And Bruno said, is that the right thing to do? Shouldn't you be doing h int in the interaction picture? Well, I was doing h int in the interaction picture, but the reason is a little bit subtle and buried in the notation. So the reason is that operators in the interaction picture evolve in the same way as operators in the Heisenberg picture of the free theory. Okay, that's the statement that it's the free Hamiltonian that governs time evolution in the interaction picture of operators. So when I plugged h int into this formula for meson decay, it was h int where all these fields were a function of x with no squiggle instead of x with a squiggle. Okay, so as soon as there's x with no squiggle, that means it's a 4 vector. So these operators depended on space and time. So indeed, they were operators in the Heisenberg picture of the free theory, not the Schrödinger picture. Okay, so that's why what I plugged in was actually hi, which is h int in the interaction picture, which means the operators are in the Heisenberg picture of the free theory. Clear? Good. Okay. So we've got this unitary operator, and like I said, it's a little bit formal. Just this t thing. It's pretty hard to do these integrals explicitly. Typically impossible in a quantum field theory. So what do we do? What we do is we just Taylor expand this exponential. So we're going to have to compute. We'll need to compute things like some final state, and then the time-ordered product of a whole bunch of Hamiltonians acting on some initial state. Okay, so these are the kind of things we're going to need to compute. And there's integrals over all of these x1s and xn's. So we got some flavor yesterday for how we go about computing this. What you typically do is each of these interaction Hamiltonians contains some fields. So you expand those fields in the mode expansion in terms of creation and annihilation operators. And then what you do is you hope that a bunch of these terms are going to vanish because the annihilation operators are going to come over here and kill this state. So we saw that yesterday for the meson decay. There was just one hi in that case, and I guess there were probably 8 separate terms that we got if we expanded in terms of A's and A daggers and B's and B daggers, but only one of them was actually relevant. Everything else just killed either this or this. Okay. So in that example, it was fairly simple, but you can see that generally it's going to be just a bit tedious, right? Because there's going to be all lots of A's and A daggers and B's and B daggers here, and you're going to have to move them through all of these operators, and you're going to pick up delta functions and the commutation relations to finally get over to here to see if it kills it or not. So it's going to be a bit arduous. So what we would like to do is just come up with some formal way that captures the tedium of this calculation. Okay, just some algorithm so that it's still going to be tedious. It's not going to save us that, but the algorithm is at least going to just sort of formalize exactly how we need to go through this operation of taking these time-ordered operators and replacing them with operators where all the annihilation operators are over here and all the creation operators are over here. Okay, that's going to be our best bet to see what survives in this calculation. So in any calculation, we'd like to rewrite the time-ordered operators as, well, we had a word for this. There was a word for operators where all the annihilation operators were this side, and we called them normal-ordered operators. Okay, remember we introduced this definition of normal-ordered operators when we were considering the vacuum energy. Okay? Okay, but it just means that all of the A's are this side and all the A daggers are this side, and similarly for the B's and the C's and anything else you have floating around. Okay, so is it clear what the goal is? Yeah. So let me just give you an example of how this works, and then I'll tell you what Wick's theorem is. So Wick's theorem is basically, just capturing the combinatorics and the formalism of how you do this in any general case. Okay, so an example is just look at the real scalar field. So phi of x, we've seen this mode expansion lots of times. We can expand this in terms of an A and an A dagger. Just to help me with some notation, let me just briefly introduce something I call phi plus and phi minus. Phi plus is going to be the A term. And phi minus is going to be the other term. Okay, let me just stress again, 4 vectors here, not 3 vectors, because these are operators in the Heisenberg picture of the free theory, okay, or the interacting picture of the interacting theory. Okay, notice that these plus and minus signs here look like they're the wrong choice because they match with a minus and a plus here. The notation is due to Pauli and Heisenberg, and I think in 80 years nobody's had the courage to rewrite it, because if Pauli and Heisenberg decided this was the right choice of plus and minus, I'm not going to argue. Okay, so what we want to do is rewrite time-ordered operators in terms of normal-ordered operators. So a time-ordered operator is this. And obviously, whether this is phi x, phi y, or phi y, phi x, depends on which comes first, x or y. Okay? So let's just make a choice and go through for that choice. So this is phi x, phi y, when y comes first. Okay? So when x0 is greater than y0. Okay, we'll expand this out. So that's just plugging in this. And so we multiply this out, we get 4 terms. Okay? Well, what does normal ordering mean? Normal ordering means that all of the a's go to the right. So the a's sit in the phi pluses. So normal ordering means that we want all the phi pluses, if possible, to the right. Okay, so what do we have? The first term only has phi pluses anyway, so that's not a problem. That just stays where it is. This term already has a phi plus to the right. So that stays as it is. The problematic term is this one. It's when the phi plus of x hits the phi minus of y. So let me just rewrite this. So it's trivially got the phi plus to the right. I'll have a phi minus of y, phi plus of x. But then I've got to add the commutator of phi plus of x, phi minus of y. Okay, so the minus term of this commutator cancels this, and what I'm left with is the honest term. And then finally, there's the term with no phi pluses, and you can't do much about that, so that's just phi minus of x, phi minus of y. Okay, all good? So what have we got? This, and this is the definition of the normal ordered product of phi x and phi y. And what we're left with is this commutator. So the difference between the time-ordered product and the normal ordered product when x0 is greater than y0 is this commutator. Well, you can just plug in those expressions for this commutator, and it's something that's very easy. Since you're all now quantum field theory ninjas, you can do this in your heads. It's just the following. Yeah, go.
So why are we so sure that the commutator is going to be time?
Sorry?
Why are we so sure that the commutator is going to be time ordered?
It's not. No. This was time ordered.
I mean, not normal ordered.
It's not. This is time ordered. This lot here is normal ordered. And this commutator is the difference between the time ordering and the normal order. So this commutator, if you work it out, is equal to this function. So it's not an operator, it's just a function.
It was my understanding that the point of this exercise was to obtain a normal ordered.
That's right. So the time ordering is not equal to the normal ordered operator. It's equal to the normal ordered operator plus something. The plus something is this commutator, and this commutator is, if you just plug in the operators, it's just a function. It's this function. Okay. So it's this that's the normal order. 1, 2, 3, 4. It's these 4 terms.
Perhaps I've misunderstood why we're doing this. I guess I can get back to it later.
So we've met this function before. This function is what we call the propagator. Back to 2 lectures ago, it's d of x times. Okay. Now we can do the same thing if the times are flipped around. Then the difference between the time-ordered guy and the normal-ordered guy, well, it's going to be the same calculation, but x and y get flipped around. Yeah?
It's in the normal form because we don't have.
How we should
The last term, that last term we have all minus a, because our goal is to put all the a to the right.
Yeah, so it's sort of exactly the same footing as this term. the goal of normal ordering is that all the A's go to the right and all the A daggers go to the left. So if you don't have any A's, you're just fine, right? And if you don't have any A daggers, which is true of this term, then you're fine. So these terms are trivial. This term was already normal ordered. It was just this one that we had to force into a normal ordered form. And this was we had to beat. Okay, so we did the calculation twice, once for x being later than y and once for y being later than x. These are the answers we get. But we'd already also defined a function that was this when x0 was greater than y0, but this when y0 was greater than x0. And we called that the Feynman propagator. So our original definition of the Feynman propagator was exactly this, depending on the ordering of x and y. So in general, okay, so remember when I introduced the Feynman propagator, I sort of pulled it out of thin air and said it would be useful later. So this is the reason it's useful. It's because from Dyson's formula, when you want to evaluate the evolution of states, you get expressions like this that are time ordered. But in order to then figure out what that term is, you want to move all the annihilation operators to the right so they start killing things, which means you want to normal order your operator. And in doing that, what appears is Feynman propagators. Okay. So if you like, this is what you pick up when you start moving A operators through everything else. You'll pick up commutation terms. Those commutation terms are of the form of these Feynman propagators. And remember finally that we had this nice expression for the Feynman propagator in terms of a Four integral. And remember, this plus I epsilon is just there to remind us that we do this strange contour that dips over one singularity and under another singularity when doing the K0 integral. Okay? Are there questions about this? So let me just point out that this is an operator, and this is an operator, but the difference between these two operators is just a function. Okay, it's just this guy here. So it commutes with everything. Okay, people happy? Yeah? Let me just give you a definition that we're going to, and Wick's formula is a bit like Dyson's formula. All the hard parts are in defining what you mean when you state the theorem, and then after that it's fairly easy. So we define a contraction of a pair of fields in a string of operators. Okay, so there's a whole bunch of operators, and somewhere within this string of operators that there's two particular guys, and the contraction we write is just putting sort of a bar over the two with little lines coming down to tell us what two we're interested in. So if you ever see this, I'll try and get my grammar right, we define a contraction of a pair of fields in a string of operators to mean replacing the operators with the Feynman propagator. And leaving everything else alone, okay? So I give you a string of operators. The operation of contracting two of them, which is denoted by putting this line that connects those two, means just removing those two operators from the string and replacing them with this Feynman propagator, which is just a function, so it doesn't matter where it sits in the string of operators. You just put it out front. Yeah, absolutely. Doesn't matter where they sit in the string, you just remove them. Yeah.
Contracting a string of operators will generally give you a different mathematical object.
It'll give you another operator. So you contract a pair of operators within a string, and what you're left with is another operator.
I mean, a string of operators is an operator.
Yeah.
And when you contract it, you get a completely different operator with nothing to do with the previous operator.
It's got something to do with it. You get it from the first operator by contracting two of them from within.
But they're not.
They're not the same. They're certainly not the same. Yeah.
Like, what's the physical relationship between the contracted operator and is this just like, oh?
It's just a definition at the moment. We'll see. I'll state Wick's theorem. You know, it's not really correct to say this. Maybe the physical relationship will become clear when we draw Feynman ideals. But for the moment, think of this as
a notational trick.
Yeah, a notational trick that's, you know, these calculations of, you know, computing, you know, some state I, time-ordered operator, some state n, they're just tedious. And what we're trying to do is formalize the tedious. So that's what this is.
So this is basically a way to help humans to do what a computer should be doing.
Yeah, exactly. That's a good way of saying it. It's just, it's trying to sort of construct the algorithm that's needed to go through these, you know, machine-like steps. Okay, finally, for a complex scalar field, you can go through exactly the same steps. What we'll do is it turns out that the contraction happens between a psi and a psi dagger. Okay? And this is now the Feynman propagator for the complex field that has a capital N there, not a little n. Capital N here. And the psi and the two psis, two psi daggers, they have no contraction between them. Meaning that if you contract two like this, you replace it with 0. This follows from, again, thinking about the time ordering of this, writing it in terms of the normal ordering, and the two fields that are both psi, you'll find that the time order product is exactly the same as the normal order. That's why it's 0. Yeah.
What if you have the dagger on the first one?
Then it's the same. It is the same.
Sorry, the last line, is that a definition or is that?
All of these contractions are definitions, but they come from, you know, you should think of the contraction as the difference between the normal ordered product and the time ordered product. And that's 0 for in this case. Okay. Now I can state Wick's theorem. So it's the following. It's for any collection of fields and let me just introduce some more notation. So I'll call them phi1 and phi2. You think of these as the same field, but just evaluated at different points in space, x1 and x2. Okay. It's going to save me lots of chalk. So Wick's theorem tells us what the what the difference between a time-ordered product of fields and a normal-ordered product of fields is. And it's the following. It's that you take any string of operators that includes phi's. We could also generalize this to include different kinds of fields here, not just the same field at different points. And then what you need to know is that the contraction between, say, phi and psi is 0 again, which should be clear because the time ordering and normal ordering is the same. They just commute through each other. So this is equal to the normal ordered product plus the normal ordered operator of all possible contractions, or the sum of the normal ordered operator of all possible contractions. So this is probably a little bit ambiguous, so I'll just give you an example to sort of clarify what this means. So an example is to take 4 fields. Well, an operator that's a string of 4 of the same fields evaluated at 4 different points. So what do I mean by this? The time-ordered product is equal to the normal-ordered product plus all possible contractions. So what does all possible contractions mean? Well, firstly, I can contract phi1 with phi2, or phi1 with phi3, or phi1 with phi4, or phi2 with phi3, or phi2 with phi4, or phi3 with phi4. Okay? That's 6 terms right there. The contraction is the Feynman propagator between x1 and x2, and is just a number. What I'm left with is an operator that I continue to normal order. So there's another 4 terms that are just like this. But then I keep going. Now I start contracting more than one pair. So I contract phi1 and phi2 with phi3 and phi4. Or I could also do phi1 and phi3 and phi2 and phi4. So these things that I'm left with are just functions. They're not operators because everything is contracted. So there's 3 different ways to contract 2 pairs. Okay, so this example is just supposed to flesh out what I mean by this statement. Questions? Wick's theorem's really dull, isn't it? Okay, proof. I'm not going to give you the whole proof because the statement of the theorem is quite dull, but the proof is really dull. The proof is the following, that it works for n equals 2, meaning when I have 2 operators here, and that's what we just showed earlier in this lecture, the difference between the time-ordered product of 2 operators and the normal-ordered product of 2 operators is the contraction between those 2 operators, which is the Feynman propagator. Okay, so it works for n equals 2, and then the proof just follows by induction for n greater than 2. So assume it works for n, and prove it works for n plus 1. Okay? It's worth, probably the best thing to do is to convince yourself that this is true. Just by sitting down, moving things through each other, And you'll see that this is true. And then the proof by induction in the general case is basically just, reimagining this. Okay? It's worth sitting down and going through, but it's not worth doing on the board. Yeah.
From the way the contraction is defined, if we consider phi to commit, like maybe in the case of volume, then we have a case where the Feynman propagator will have something like e to the minus I equal e to the plus I.
E to the minus I.
Because if phi, the contraction between phi x1 and phi x2 is the Feynman propagator of x minus y.
Yeah.
And if phi x1 equal and phi x2 equal, then we want to say that the contraction will also be equal to that.
Oh, good. So phi. Let me try to see what you're saying. So just because phi's are bosons doesn't mean they commute, but they do commute outside the light current. Okay, so if meaning that if x and y are space-like separated, they'll commute. So then the question is, do you see that in the Feynman propagator? And the answer is yes. The Feynman propagator has that. Is that me right?
Yeah, because my point was about the definition of the time ordering. Because if you define the time ordering as the way you define it without considering the fact that in the case where we deal with Fermion, we can put the minus sign there, then I have a problem here when we define the contraction to be equals to the Feynman propagator of x minus y. Because if that is the case, and if we flip over, like in the case of time ordering, flip over, we have a case where we expect something like e to the x equal e to the minus x.
So it's what you're saying, that if they're space-like separated, it's not a Lorentz invariant statement. Which one comes first? Is that?
I think you might be worried about the fact that with bosons and fermions you have different, maybe a minus thing.
That's true. So there are minus signs that will arise for fermions,
Yeah.
and we'll just deal with that when we get there.
Is the question about whether the Feynman propagator is an even function of x minus y?
It should not be.
Because if you're right, is that your question?
It should not be.
It is an even function, right?
It is. No, I don't think it is. It depends on which one comes first, x or y, or x. I don't think I quite understood the question, but let's just chat afterwards and we'll understand. The answer certainly is that any property you want it to have, it will have. If you're worried about things commuting outside light curves. So we'll just have to sit down to secure it. Okay. Other questions? Let's see how this Wick's theorem works in a slightly more complicated example. We did meson decay before. We'll do a slightly more interesting example now. But are there any questions? Okay. So the example we're going to do is the scattering of two particles. Again, in this theory that has a single complex scalar field and a single real scalar field. So an example is nucleon scattering. By which I mean that we take two psi particles and we want to know the probability, really the cross-section, for them to scatter into two more psi particles. Okay? I'm not actually going to compute the cross-section, I'm going to compute the quantum amplitude. You then have to square it to get the cross-section. And I think you've done these kind of calculations with Malcolm already. Okay, so what does this mean? It means that I've got some initial state which consists of two nucleons, which I'll give momenta P1 and P2. I'm going to write my initial state in this way. Okay, so I act with two creation operators for the psi particles. They're the B's, and these are these relativistic factors that I have to put in for normalization. The final state is also going to be two nucleons. But we're interested in some scattering process. So in general, they can have some different momenta, so I'll call them P1 prime and P2 prime. Okay, two guys come in, two guys go out. Is there a question?
Vector hats, or in this case.
Ah, is that right? Yeah, sorry. Yeah, thank you. Thanks. Okay, so what do we want to compute? We want to compute the probability for this state with some momentum to turn into this state. So actually, if these momenta are exactly the same as these momenta, there's something trivial that can happen, which is the two particles come along, they don't do anything at all, and they keep going along. Okay? Just so we exclude that possibility because it's boring, I'll consider not the S matrix, but S minus 1. Okay? Remember, the S matrix is the exponential of that Hamiltonian. When you expand out the exponential, there's a 1 plus interesting stuff. I'm going to get rid of the 1 in that expansion. Okay, because it's boring. Okay, so we want to compute this, and we need to figure out which order to compute it at. Well, it should be fairly easy to see that at leading order, that means that when you expand out the exponential to be 1 plus h, that you're never going to get this I to turn into this f. In particular, one factor of h always has a creation or an annihilation operator for a meson, but neither of our states have a meson, so it's just going to kill it. So it's actually at second order. That means order g squared that something interesting is going to happen. Okay, and we take this one off just because we're not interested in processes where nothing happens. Yeah, it's going to be that same psi star psi phi. Yeah. So what do we get? We get expanding out the S matrix to second order. There'll be something with a g squared. There's a minus I, which was sitting up in the exponential. There's a half because we're doing a Taylor expansion for an exponential, and the quadratic term comes with a 1 over 2 factorial. So we get h squared. The interaction Hamiltonian is evaluated at 2 different points, x1 and x2. You then integrate over those points, but you have to time order this guy here. Okay, so what do? We do Wick's theorem. So Wick's theorem says that the time-ordered guy is equal to the normal-ordered guy plus all possible contractions. Okay? Plus all possible normal-ordered contractions.
So when you call scale,
It's the same theory we've been considering.
yeah, I was just wondering.
Balance.
No, it's just making sure.
H equals G psi star. C.
Yeah.
Other questions? You guys good? what's going to happen? Well, there'll be that first term. The first term is where everything is normal order. What's going to happen when everything is normal order? Well, in particular, there'll be some annihilation operators phi that sit to the right, but they're witters, because that operator is removing a meson from the state, but there is no meson in the state, so that's just going to kill us. Because we have two nucleons coming in. So somehow we've got to get rid of these phi's, and the way we're going to do that is to look at the term in Wick's theorem in which this phi is contracted with this phi. Okay, what that means in reality is that we've taken the A dagger from here and we've commuted it past the A from there and then got something new. So there's a term from Wick's theorem which looks like okay, so we'll leave the psi's alone. They're normal ordered because this is a term on the right-hand side of Wick's theorem where we've contracted these two phi's. Yeah, thanks. Yeah. Okay, so this term's going to be there. You can convince yourself that this is the only term that's going to be relevant from that first bunch of contractions. So what this term is going to give us is x1 psi of x1, psi of dagger of x2, psi of x2, p1, p2, times by, well, it's going to give us this times by this contraction, but let's just look at this. The contraction we'll put in at the end, okay? Well, I'm not going to go through this on the board, but you should just check that, if you just plug in the mode expansions for psi and psi dagger and get them to cancel the B plus daggers that are here and the B's that are here after you've pulled out the creation operators, this is equal to two terms plus another two terms where you swap around x1 and x2. Yeah, almost certainly. Yeah. Okay, so I'm not going through it, but you can see how you get it, right? You sit down and it's a bit boring, but you just start moving B's and B daggers through each other. Sorry, this one?
Yeah.
This means that it's not written very well, but it means that it's exactly the same as these two terms, but where you replace x1 with x2. Okay, so there's another two terms.
Okay.
That are exactly the same with x1 and x2. So plugging all this in, if we compute the amplitude for this initial state to go to the final state at order g squared, what we get is minus I g squared over 2 is the integral over d4x, all of these exponentials plus the x1 minus x2 times by the propagator so this propagator came from the contraction of the two phi's, and I'm just writing down in full what the propagator is. Okay, so you can now convince yourself that the terms with x1 and x2 exchanged are actually exactly the same as these two terms under the integral, because x1 and x2 are on the same footing. So that's going to cancel this factor of a half. Then, what do? Then we do get this right. Then we do the x1 integral to get a delta function. And we do the x2 integral, and we also get a delta function. So we're going to get two delta functions from doing these two integrals. We're left with this guy. And so at the end of the day, and then, of course, one of those delta functions allows you to do this integral. Okay, yeah.
The aim of doing this arranging a time order into a normal order and contraction is so that the normal order expectation value will vanish. But I see you still calculating the normal order there. Why? Because necessarily the first line on the right. If that thing there is in normal order, then it's 0.
No, it would be 0 on the vacuum. But this isn't the vacuum, so I've got two B dagger operators sitting here. And so the game is to then move the B operators, the annihilation operators, from this expression through those two B dagger operators that come from the vacuum. Let me say it another way. If you take an annihilation operator and you hit it on the vacuum, you get 0 because it takes away one particle. But this state had two particles in. So there's the two annihilation operators from here will just take away these two particles and leave you with the vacuum. It won't kill it, it will just take you down to the vacuum.
We pulled out the propagator because it's not an operator, right? It's just a propagator.
Yeah, then that's when you're allowed to pull it out and then put it in at the ends.
And so everything we contract will always be able to just sort of throw off to the side and deal with this normal order operator. Yeah. And so you say we'll get the two annihilation operators. Is there a way to, like, there's still a lot of terms up in that normal ordering, right?
Okay.
Yeah. There's not a further algorithm. I mean, we're building.
Yep, there's a really beautiful algorithm we'll get to next, which is that you forget all about Wick's theorem and you just draw prefixes.
Excellent.
Shouldn't that expression be P1 minus P1 dash minus M square and
Yep,
P2 minus P2 dash?
Here?
Yeah. Should be P1
An
minus.
extra dash sign.
It's not symmetric in P1 and P2 then.
I need to scale a second term as well.
Sorry, yeah, P1 minus P1 dash.
And P2 minus P2 dash.
P1 minus P2 dash. Yeah.
P1 minus P2 dash.
P1 minus, yeah, it doesn't look symmetric, but if you take into account this delta function,
Okay.
it is.
We have UDI, and the checks on next to. Is there 4 terms there or 3 terms? Because shouldn't you have, like, I'm guessing those are contributions from ST and U channel, respectively?
There's no S channel.
Because, well, because they're the same particles, right? But
So there's a T channel and a U channel. This is basically T channel, and this is U channel.
And
Sorry,
yeah.
this is U channel. All of this is T channel.
okay, so if you had like psi bar psi, you'd have 6 E terms there.
Okay, psi bar psi, no, I think there's a T and an S that not used.
Is there any time that all 3 contribute? Anyways, it doesn't matter. It's perfect.
True scattering, I suspect not to use true scattering, but I'm not sure. Not in this case.
Right. I'm assuming you're sparing the second P1 minus double P dash.
Yeah, thanks. This formula was more wrong than right. Morally. The right one is in the notes. Okay, any other questions? Okay, so you kind of get a feel for how this works, right? And there's sort of several of the questions have illustrated. You've also got a feel that it is sort of tedious to go through these steps. So there's a way to alleviate the tedium just a little bit by drawing pretty pictures. And these pretty pictures correspond to mathematical equations, things like this. And often it's very difficult to evaluate those equations, but it does at least put a bit of childlike fun back into actually getting to these equations. Okay? So that's what I'm going to explain now. Yeah, there are no singularities in the square bracket. It's an issue to do with these T channels and U channels. Had we done the psi bar goes to psi bar, one of these terms would have a singularity. And I've not yet decided whether or not to comment on this in the next lecture, or whether you guys are going to do it in a tutorial tomorrow afternoon. I think it's probably going to be a tutorial. Yeah, just to elaborate on Tibra's point, which I should have done before I rubbed this off, the denominators here are never singular. Okay, just, you know, they look as if they have a possibility because it's something p squared minus m squared. But if you figure out what p's are kinematically allowed from these particles coming in, you'll see that it never diverges. However, typically if you do particle-antiparticle scattering, then you do see a divergence in the denominator. So you see a 0 in the denominator, a divergence in the amplitude. And that means something physical, which I think Malcolm has already commented on, the fact you get resonances and scattering amplitudes. And, okay. So that kind of behavior is all going to appear in these calculations if you do particle-antiparticle scattering. And so at some point in the next 2 days, either in a homework or a tutorial or on the board, you'll be led through this phenomenon. Okay. So, pretty pictures. Pretty pictures have a name. They're called Feynman diagrams. So, instead of working with Wick's theorem, we'll instead draw pretty pictures. Okay, so what I'm going to do is just tell you the algorithm to draw these pictures. The point of these pictures is that every one you can draw down is in one-to-one correspondence with the kind of terms that arise in Wick's theorem. Okay. Now that may or may not be obvious to you after I've told you the algorithms to draw these pictures. And again, it's one of these things that it's best to convince yourself just by sitting down and doing a few examples. I'll do the example of nucleon scattering on the board, but you know, these are really just capturing the combinatorial tedium of working through Wick's theorem, but in a nice way. Okay. So the terms that arise in computing the non-trivial part of the S matrix are in one-to-one correspondence with with the following diagrams. Okay, so these are the rules for drawing a Feynman diagram. So the kind of process that we're interested in is some number of particles in the initial state and some number of particles in the final state. So for every particle in the initial or final state, we're going to draw an external line, by which we mean sort of a line that, if you like, you can draw out to infinity. So draw an external line for each particle in the initial and the final state. What's more, if the particle has a charge associated to it, so the psi particles come in either psis or anti-psi particles, then we're going to draw an arrow on the line. So draw an arrow on the line, for psi particles to denote its charge. Okay, so we're not going to draw lines for the mesons, because the arrows are going to correspond to charge, and the mesons are real and therefore don't carry any charge. And we just need a choice for this. So the choice we're going to take is that if we have incoming psi particles, if we have psi particles in the initial states, we're going to draw the arrows coming into the diagram. If we have psi bar particles in the initial states, the other way. So choose, so this is just a convention. Choose incoming or respectively outgoing arrows for psi, respectively psi bar particles in initial state, and the opposite for F. Okay. So we've got a sort of a bunch of disconnected lines at the moment, one for each particle coming in and one for each particle going out. Now we join all these lines up. And we join them up using vertices and the vertex is going to be the following. Okay, by the way, I've just introduced some new notation here. Just to clarify, if there's mesons, I'm going to draw a dotted line. I'll do this for the external lines as well. And if they're nucleons, I'll draw a solid line. Okay, so typically it's useful to keep track of what field we're talking about by having different lines. People use wiggly lines or jagged lines or various possibilities. Okay, so this line represents phi in the interaction. This line represents psi dagger in the interaction, and this line represents psi. Okay, and the reason we've got a trivalent vertex is precisely because our interaction term was cubic in fields. Okay. So if we had a term that was quartic in fields, we'd draw pictures with 4 legs all meeting at a point. Okay? No, there was just, for example, if we had a single real scalar field with a phi to the 4 term, there'd just be that 4 lines meeting at a point, not wow. And we'll deal with that maybe in the next lecture.
Are you writing the ingoing or outgoing? Sorry, the initial or final state, because doesn't that change whether your phi or phi dagger or psi or psi dagger is going
So this is neither. This is a vertex which I've now got to attach to those external legs. Okay, so I have a bunch of external legs that weren't connected, and now I've got to somehow join them together using this vertex. The really important thing is that the arrows kind of follow through, and that's something we're going to have to keep in this. That's representing the conservation of charge between incoming and outgoing. Okay, so let me just give you some examples. So these are the rules for drawing the picture. And then I'm going to give you the rules for associating to each picture a mathematical formula. So the psi, the 2 psi particles go into 2 psi particles. Well, we have so this is 2 incoming psi particles, this is the 2 outgoing psi particles. Somehow I've got to join all this together. So this is one way I can join it together. I should also just label these. It's useful to know which particles we're talking about coming out, so we'll just label them with the momentum that we've chosen for those particles. So that's one way. There's another way which looks the same, but where just the labels have been split. So this diagram is different from this diagram because these particles here are big. So these 2 diagrams, but there's also more complicated diagrams that we could draw. So we could draw something like the following. Okay. So as you start to let your imagination run wild, you see that there's actually an infinite number of increasingly complicated diagrams that we can draw that have these 4 lines connected in some way. Okay. Of course, if I label these with momenta, I could also have 2 diagrams for each where the momenta flip. Okay, so are the rules about how to draw pictures clear? Okay, yeah.
Diagrams mean anything?
Mm-hmm. Yeah. There are nice words you can wrap around, which I'll. Okay, so now we want the rules to associate to each of these pictures a mathematical formula. Okay, so there's 2 steps here. Firstly, you should convince yourself that each of these pictures is in one-to-one correspondence with the terms that are coming out of Wick's theorem. And secondly, you should convince yourselves that the formulae I'm attaching to these pictures are exactly those that come out of Wick's theorem. And that may be more or less obvious to you, depending how familiar you are with these things. Okay, so here's the way you associate mathematical formulae to these. So add a momentum k, to form momentum, to each internal line. Okay. So in these diagrams, there's only one internal line. It's this dotted one. These diagrams have many more internal lines. This one has 4. Right? It's got this guy, and although this looks like it's connected, it's really 2 because there's one that goes from here to here, and one that goes from here to here, and then there's this guy. So there's 4 internal lines in this diagram. Okay. You should add a different k to each internal line, not the same k. Okay. So to each vertex, write down a factor of, and again, this is specific to this particular scalar Yukawa theory that we've been considering. Okay, so each vertex comes with a g squared, factors of 2 pi and I, and then there's a delta function which sums over the momenta of the 3 lines that are coming into that vertex. Okay, so here it would be the momenta of this one, and this one. Each vertex gets g squared. Nope, that's wrong, isn't it? Thanks. Yeah, each vertex gets g, absolutely. Yeah, although I am going to keep writing things as minus I squared, just to remind you to minus I in that interaction. Yes, sorry, you're absolutely right, it's g.
So the reason why you don't have pictures that look like just 4 lines going in, 4 lines, or 2 lines going in, 2 lines going out, is that each vertex has to have all 3 fields.
What kind of pictures?
No, I'm wondering, like, if you just had like a cross, is that not allowed because you have to have each field?
Oh, there's no vertex in this theory where 4 psi particles interact directly.
Okay.
And so that's why you don't have. You could have kind of the thing where they miss each other, but that's the same as that. And that's we got rid of because we were interested in s minus 1. But yeah, in this particular theory, there's no vertex like this. What it's really saying physically is that in the Lagrangian we wrote down, the psi particles don't interact directly with themselves, they interact through the meson, and then the meson has to go and interact with more psi particles. So it's going to be this 2-step process, and that's sort of what we see here. Psi interacts with the meson, interacts again with the meson. Did that answer your question?
Yeah.
Okay, so finally, for each internal line, with momentum k, write down the factor of the integral over that momentum times by the Fourier transform of the propagator for that particle. Okay, so what do I mean by this? This is just the, all these propagators were written as integrals over d4x anyway, so we just strip off that d4x. So this is the Fourier transform of the Feynman propagator. Okay. So the only difference between having a phi particle or psi particle is whether it's little m or big M. They were the masses of the particles. Okay, Is this clear? The e to the I.
Right, I'm just wondering if it's, I mean, it's,
So-
are you
so
including
the-
it somewhere? Or?
Yeah, so the Feynman propagator was basically the Fourier transform of this.
Yeah.
It was this multiplied by e to the I k dot x minus 1.
Yeah.
We've got rid of that. If you think back to the calculation we just did for nucleon scattering,
Mm-hmm.
there were all of these e to the I p1 minus p1 prime x1 minus, there was all of this stuff. So at the end of the day, we integrated over x, and they all gave delta functions. So somehow, this is what's going to give rise to those. Okay? So this is kind of doing all this tedious grunt work for you, and just giving you quite. So let's just go back and look at this this nucleon scattering problem and apply these rules to it and just see that we get the answer that we got during the hard work.
Yeah, in your integral, you did power of 2 pi.
Oh, thanks. Yeah, that should be good.
So, where did the x's actually come into this then? With these Feynman rules you written down?
So these are not Feynman rules in position space, but the x's have basically disappeared. Even in,
You put, for external lines, you also write down a momentum.
but that's exactly what we did in Wicks's theorem. Wicks.
So your rules say add a momentum to each internal line, but you're including the external lines as internal lines now. Are you labeling the external lines?
Oh, so yes, sorry. So the external lines I also want to label by the momentum of the particle.
Okay.
And then the internal lines I give an arbitrary momentum to. And we see that it's arbitrary because ultimately I'm going to integrate over all possible momentum of those internal lines.
I just don't want to be confusing between internal and external lines.
Yeah, so they both have momenta associated to them, but you integrate over all possible momenta for the internal lines, whereas the external guys, you know what the momenta they are, that's the your detectors that don't see that. So nucleon scattering revisited. Okay, so what did we compute earlier in this lecture? We computed psi plus psi goes to psi plus psi, but we did it to order g squared. Okay, so at order g squared, the Feynman diagrams that contribute are just 2. Okay, they both look the same. But they have the momentum on the final states exchanged. By the way, we were saying words earlier like ST and U. This is called a T channel, and this is called a U channel. And there's something else called an S channel that you'll see in a tutorial exercise, but it's not that important. It's called T because it sort of looks like a T. Forget about S and U. Oh, good. So the S channel diagrams look like this.
Yeah, so why in this case?
Because we've got 2 psi's, and that ain't a vertex that's allowed. It's because the arrows don't be solid. Okay, so the vertices that are allowed have the arrows solid. So if we had a psi and an anti-psi, we could draw a diagram like this. So one of the problems you'll do is the scattering of psi anti-psi. Okay, there's 2 vertices here. So these are the diagrams that arise at order g squared, as you said. Each vertex gives 1g. Anything more complicated is going to have higher powers of g. So as long as you're in a weakly interacting theory, drawing more complicated diagrams is considering terms that are less and less important in the perturbation expansion. Okay? So typically you only need to consider the few simplest diagrams, and depending on how precise you want to be, you may have to consider more and more diagrams. By the way, somebody asked me yesterday, are these series convergent? The answer is no. They're never convergent in any interacting quantum field theory, certainly not in 4 dimensions, perhaps some special ones in 2 dimensions. So the series always diverge, but you can make sense of that. It's not something you have to worry about. For example, in QED, the dimensionless number, which is the coupling constant, is 1 over 137. Okay, so the first diagram is of order 1 over 137. The next diagrams are of order 1 over 137 squared, and so on and so on. The series gets more and more and more convergent until you hit roughly the 137th series in the perturbation expansion. Okay. And then the coefficients which sit in front of 1 over 137 to 1 over 137, they start to increase again. So as long as you're happy to get QED to an accuracy of 1 over 137 to the power of 1 over 137, you're basically fine. Okay. There's lots of, sorry, I wanted to keep this. And there's lots of interesting mathematical physics and even physics associated with these kind of stories, but we're not going to go into them in this course. Okay, so let me just use the rules and write down the answer. So when I draw these pretty pictures now, each one is actually a mathematical equation. Okay? So things like plus and equals make sense. There's a minus I over g squared. Why is that? It's because there's 2 vertices. There's an integral over d4k, 2 pi to the 4. That's coming because I've got a single internal line. There's a value of the propagator for that internal line. It's a little m, not a big M, because the internal lines are meson. And then there's 2 delta functions coming from the 2 P1 minus P1 prime, P2 plus K minus P2 prime, coming from the 2 vertices. So this is the sum of momenta going to this is 0, the sum of momenta going into this is 0. That's these 2. And then the second diagram K. We do the K integral with the delta functions. And what we get is exactly the same expression that we had before. Yeah, Tibra.
Arbitrariness in the sign of k in. Yeah, I've put a k here with a particular. So does it matter if I switch around? If I see k as going upwards instead, would I?
Because you're going to integrate over.
Right.
This is a k non-range.
So I should get the same.
You get the same. And that internal momentum is completely arbitrary, precisely because you use it. Okay, so a few things to say. Firstly, this is a whole lot nicer to do this way than the Wix thing. We can all agree. If it looks a bit too magical to you, I'm going to set a homework exercise to calculate various other processes within this theory. If these Feynman diagrams just appear magical to you, then do the calculation both ways, using the Wix theorem, using the Feynman rules. And you'll just sort of see that all of these Feynman rules are doing are encapsulating the boring algorithmic things that you have to do in Elixir. So they're really not that much. It's just a very nice notation to capture. What else to say? Yeah, a few things. Firstly, now we've got these nice pictures. People have been asking me, should we assign physical meaning to these? Yeah.
So within the vertex, you write down these terms and then you multiply them together, and then you add one diagram to another.
That's right. Yeah.
Okay.
Yeah. Yeah. So when I wrote down those 5 rules, every single thing that you multiply together for one diagram. So for example, for each vertex there's a delta function, so I just multiply these delta functions. Yeah. So this whole thing is the first diagram that you have.
So you're missing a square in the second term.
I'm missing a square, thank you. But the nice thing is that I missed exactly the same square when I did it using Brixton. It really does get exactly the same answer. Okay. So the question about whether these things are physical. Well, it's obvious that there is a very nice physical interpretation that you can assign to this. 2 nucleons come along, and this nucleon spits out a meson, and it hits the second nucleon, and then off they go, and they've changed their momentum because they've sort of fired mesons between them. And it's not a bad sort of heuristic way to think about what's happening in particle physics. Well, one thing that's important to notice is that these particles here all satisfy that p squared is equal to m squared. This is because they're real particles which we hold in our hand, and the 4 momentum squared is equal to the mass. If you look at k, what the momentum of this guy is, well, in this case, it's fixed by these delta functions. So k is equal to the difference in this momentum and this momentum. Those delta functions never have k squared equals m squared. Okay? So the guy that's moving through here, this meson, it doesn't obey what you think it should obey. It doesn't obey that its 4 momenta squared is equal to its physical mass squared. Okay, so there's words we say to this. We say that these guys are on shell, and we say that this meson here is off shell. Off shell means it doesn't obey this condition here. So again, if you want to drape nice words around this, you say that what's happening here is that this is a virtual meson. It's sort of allowed to propagate for some time because of Heisenberg uncertainty relations, so on and so on. Okay, how much you want to assign meaning to these words is really up to you. This is the mathematics, and there is some sort of, I think, pretty much correct words that you can drape around these diagrams and these equations. But it's a personal choice as to whether you're comfortable with that. One other thing to say, which is that these diagrams I told you, yeah, please.
So the reason we got these diagrams is because we put side dagger 5 in the potential interaction.
That's why we got vertices of
so that interpretation all hinges on the fact that happens to be the Hamiltonian interaction and the interaction.
So that's an interpretation that applies to this theory.
Right.
Other theories.
So, but was that one motivated? Or is it one motivated in other theories, other quantum field theories? The term that looks like that and gives rise to diagrams like this, which we can interpret.
The terms that arise in quantum field theories are always, not always, certainly the terms that arise in field theories for particle physics, for standard model, are always either of this type, or a cubic interaction, where you say exactly these words, or of this type, and this also has an interpretation. It's the 2 particles come along and actually just bounce.
Is there a good reason for having all these diagrams?
Yeah, it's the reason that I sort of explained in a very hand-wavy way a couple of lectures ago. It's because anything higher is what's called an irrelevant operator, irrelevant term in the Lagrangian, and just doesn't matter. It's literally irrelevant to low energies.
Okay.
So it's because you start to write increasingly more complicated terms. They're suppressed by some mass scale that's typically a high mass scale.
So like a 6-point vertex just doesn't make sense, right?
It makes sense, but you'll get some coupling constant divided by, we call this lambda. divided by some mass scale, and this is typically the Planck mass or the gut scale.
Right.
Or,
So it's just so huge that we
yeah, it's way, way down. It's just not something we have to worry about. It's typically the scale of any physics beyond what you sort of explored already.
So
Aaron, you have a question?
Yeah, so regarding the physical reality of these terms, so you get the, like all of this thing comes from essentially evaluating the sandwich of the final state, the initial state, and the time evolution operator.
Yeah.
So you write the time evolution operator, you expand it in terms of into a sequence of products of creation and annihilation operators.
That's right.
So it seems like if you look at a product of creation and annihilation operators, there's no like order to it exactly. Like they're non-commutative, but it seems like
what's happening in that language is that you have, let's take this side of side. So there's a side of side there and a side of side there, and a whole bunch of stuff in the middle. Okay? The term in Wick's theorem that's giving rise to this has a creation of a meson particle and an annihilation of a meson particle right next to each other. So somehow what's happening is that when you do this, it's restricting to a state of this type.
Right.
Which is kind of like going from, two mesons to a. So the same language that you might want to drink around this picture is already there in these four messages.
And yet it seems like if you did the same thing for a Stirner-Locke experiment, right? You could say like you have some term like if you're going from like a spin up state to a spin up state, you could end up with a term where like a spin X state and a spin
I see what you're worried about. Those
like it seems like well let's put it this way. I think we can all agree that this is a stupid way to think about Stirner-Locke experiments. And if you can't agree, then I'd like to hear why.
Yeah, and what's all right. Good. Okay. Like I said, what's happening here is that in the middle, it's not really an eigenstate of the free Hamiltonian that's in the meson state, precisely because it doesn't obey this on-shell condition. So you're right. It's then you drink more words. You say it's a virtual particle, not a real particle. You can keep making up words. In some sense, it doesn't matter. It is a good intuition to have that that's what's going on, but it's not necessary. And these are equations that are
Also, in the middle, the Hilbert space is not a Hilbert space of free particles anymore.
Yeah, exactly. There's one last thing I want to say, sorry, I know I'm running on. There were diagrams like this, which I told you would be suppressed because they're ordered g to the 4, in this case 1, 2, 3, 4 vertices. And it's true, they're down by g to the 4, but there's a coefficient in front of them which is infinite. And it's infinite because, here we have to integrate over the momentum of all possible internal lines. Here we integrate over this momentum, but it's easy to do the integral because there's a delta function from this vertex which tells us exactly what this momentum is. Here you have to integrate over this momentum, this momentum, this momentum, and this momentum. There's two delta functions which are telling you what they are, but it turns out once you impose all the delta functions, including these, there's one which is unconstrained. So there'll be an integral over one particular momentum, which is basically a momentum that's running in this loop here. And that integral will give it to it. Okay? So how do you deal with that? Well, in this course, we're just going to ignore it. We're going to keep going through these sort of leading order calculations. We'll deal with it using the techniques of renormalization in the next course.
So just another note. Those are called tree level diagrams, and there's a loop.
Yeah, I was just going to say this. So there's names associated. It's the leading order guys from tree level, because as you can see, they really look just like trees. These guys here are called loop diagrams because they have. So the leading order calculations are usually called tree level calculations, and they're the ones that are nice and finite and agree to experiments up to the order that you would expect. These guys you have to work a bit harder to understand, but it's understood. Okay, so sorry to go on so long. I'll leave it.